So my name is, you guys know my name by now, Roger Sinfort. I'm with Memorial University. A brief biography in terms of who I am. I am a professor in the Faculty of Science and Technology at Memorial University, and I teach courses on groundwater contamination, environmental pollution prevention, and soil remediation. I received my Ph.D. from the University of Nebraska in environmental chemistry. In my primary research and professional activity, I involve fate and behavior of contaminant, contaminated site investigation and remediation, and also the use of chlorine dioxide combined with UV system for remediating NAPL contaminated groundwater, and also do a lot of research using electro-coagulation and nano bubble technology to reclaim a variety of wastewater streams, and as well as evaluating various forward osmosis membrane suitability for water desalination. So, all right, I'm going to go forward here and get started on my presentation. So the title of my presentation is Landfill Leachate as an Alternative Water Source for Alberta Oil and Gas Development. And I would also like to thank the other person who worked with me on getting that presentation organized. And at this point, yeah, I got it. So her name is Carrie Baldwin. She's also a regulator at Alberta Energy Regulator in Calgary. For the acknowledgements, would also like to acknowledge Baker Hughes and BP Amoco Canada, because we have very enlightening discussions when we're getting that project organized. They're very, very useful because they're a very, very practical person and also have a lot of technical knowledge that Carrie and I didn't have. So therefore, they fill in that gap in terms of providing the technical support in terms of answering some very, very good questions that we didn't have the answers for. Now a quick little overview of how my presentation is going to unfold. We'll look at the problem statement. Okay. Getting used to the clicker here. So problem statements and opportunities, and what are the primary objectives, and also how we went about executing, carrying out the study, and also cover a section on data handling and analysis, because we had a bunch of data sets and we had to do some statistical analysis on that, and summarize for you guys what the main findings are. And when you do those kind of study, very importantly, it's the cost-benefit analysis. So because that's the bottom line from a practical standpoint. So there's also a section that address that, and of course some limitation and delimitation. And at the end, a bit of wrap up all the important point associated with the finding of the projects. All right, so in terms of some of you are a bit more expert than some other one in terms of when we talk about fluid types, when it's come to oil and gas for drilling, they're pretty much three main type. So you have the water base, which is pretty much the most commonly used now in Alberta. Okay, so the acronym is WBDF. So we also have the oil-based type of, so which used to be used more oil in the past. So there's a shift now, moving away from the oil-based because of the environmental concern and also in terms of the handling of that. Move more toward the water-based, which is more environmentally friendly. And we don't use much of the pneumatic in Alberta. So as you could see here on the water-based, so one of the ingredients, let's say water-based, is that makes use of a lot of fresh water, okay, and also make use of some gel chem, some polymers, and also sometimes some calcium treated kind of input substances. But this is the big one, and that will be the primary focus of the presentation. So now, when we talk about the choice of drilling fluid, all right, when in oil and gas, so it depends on several factors, but the most important one associated with the well design and what kind of formation you're dealing with, and pressure, chemistry, and temperature. So which means that what are the well conditions, and very importantly also what are the environmental restrictions and also concern, because at some point in time that drilling fluid will the drilling program essentially you'll be generating drilling waste, and therefore how the most effective way in terms of handling that drilling waste. So therefore, the input is very important in terms of the choice of your drilling fluids. Okay, and also the fluid technical performance and potential in terms of its effectiveness. So this is where the experts, they come into play, because that's where they have the knowledge in that regard. And of course, you have the costs associated with what kind of drilling fluid programs that you come up with. So what are the current issues? The problem is that there's a lot of on the water-based drilling fluid program. You use a lot of fresh water is used, and therefore that tends to create some perception in terms of oil and gas as a sector. It's not really that sustainable first, but also not that environmentally friendly. So therefore, that perception is very, very important when it comes to the public domain. So although the fresh water is a preferred fluid for water-based drilling fluid, and we'll in the formulation we'll see, we'll see what what does that entail in that sense. All right. So now the next important thing is water scarcity. So in Alberta, the last few years we've been experiencing some water scarcity. So therefore, some competition between oil and gas and also various sectors in society in terms of getting access, and not only access but enough fresh water, for what the application will be for. And there's also another issue: it's cost of allocation. And for oil and gas, because of the scarcity, like anything else, because water is a commodity, you have the notion of supply and demand, and increasingly year after year, the cost of allocation to oil and gas, particularly, the price goes up, and it goes up significantly. So therefore, there is a need to find another alternative to using fresh water. So, and also, Alberta energy sector use about 10% of fresh water, which is very, very significant. So when you look at it from a volume standpoint, we're talking about millions volume of water. So if that can be reduced, okay, from a public relations standpoint, that will be tremendous. but also in terms of making the industry more sustainable. So that this is also very, very pragmatic in that sense. And 1% of fresh water used, from that 10%, 1% is used in drilling operation. So I attached a number to that. So this amounts to about 10 million cubic of fresh water, okay, on an annual basis. So that's a lot of water. And if anything else, it's going to keep going up from year to year. Okay, so freshwater demand increases in all sectors, while availability decreases. So that's what we have a scarcity, and also very, very important, it's where regulations are going. Okay, so right now the push is to have, in oil and gas as much as possible, not using fresh water. And I'll give a definition of fresh water in a few minutes. All right, so therefore, if the other source of water that can be used, for example, wastewater, wastewater streams, and one of the streams in that sense could be, leachate coming from landfills, and that will be down the road, more likely that will be the preferred options for oil and gas. But also, this is where, with the upcoming regulations down the road, I'm not sure when, we'll push oil and gas toward using pretty much wastewater, okay, in the drilling fluid program. And also some concern in terms of, because of water scarcity, so on and so forth, potential adverse impact on the ecological system, and also social and economic imperatives. So that's why, try oil and gas sector to try to make the program somewhat as sustainable and as environmentally sustainable and economical as possible. So to give you guys a little bit of context in that sense, in terms of competition for water availability, and the issue that may lead down the road. So the null hypothesis here: could landfill leachate replace fresh water in the formulation of WBDF? And of course, the alternate, it's the converse. Landfill leachate wouldn't be, because of performance, be able to replace fresh water. Now, when talking about fresh water, essentially, we're talking about pretty much like potable water, water from lakes, water from rivers, and also groundwater. But it's groundwater pretty much up to about 150 meter depth, because a lot of time that's where you have aquifers, and you have also the water quality is pretty good. Okay, it's not salty, and it meets the criteria to a certain extent as for potable. So when we talk about fresh water, you can equate it to potability, i.e., very, 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 very good quality. In terms of guideline, we considered when we undertake the study. So we looked at the most stringent guideline, okay, which is Alberta T1 guideline, which is the minimis criteria. So which is prescriptive, okay. So the idea is to protect, okay, of the most sensitive situations, and the target, the endpoint in terms of concentration are provided in the criteria. All right. So in that case, that's what we're using in terms of standard. And in terms of exposure pathways, the guideline consider that, okay, and receptors, and that would be a function of the land use, at the site. So if the land use is, or during the drilling, if it's agricultural, or if it's green space, i.e. natural, so therefore the guideline, address that. And usually it's the lowest value of the four land use. Okay, a lot of times that we try to consider. Okay, so those are the typical land use we have. So we have agricultural, usually natural tend to be the most sensitive, and the least sensitive will be industrial. And also the criteria take into consideration two type of soils, fine and coarse grain. Essentially, when you talk about the Alberta T1 criteria. What does that mean? Essentially, it's risk-based. Okay, so which means that it's scientific, and there are also some other factors that I haven't mentioned here, but it addresses to a very practical ways. Okay, how to protect the environment, but also pathways and receptors. There are also one other criteria, which is Alberta Tier 2. Sometime in some situation when you're doing drilling and handling the the waste, so on and so forth. So you may move away from the Alberta Tier 1, but you have to gather more information, okay, in order now to make a scientific and a business case to the regulators in terms of why you want to move away from Alberta Tier 1 and you want to adopt Alberta Tier 2. So the primary objectives is to ascertain, is to determine whether or not Class 2 leachate characteristic essentially within the criteria, and perform cost-benefit analysis, and do a quick kind of risk analysis, in terms of potential risk to human health and the environment, and also, of course, try to determine what will be some of the limitations, okay, associated with using the landfill leachate. All right, so let's talk about a little bit about the landfills, how they're classified in Alberta. So we pretty much have 3 classes of landfill. So we have Class 1, okay? So Class 1 is not included, wasn't included in the study. And we have, Class 1 is very hazardous kind of material, okay? So highly contaminated. So we have Class 2 that, and that's the one we focus our primary attention on, because that's the most landfills that we have in Alberta. Under that umbrella, you have municipal landfill, all right, and you also have waste streams that cannot go in Class 1, cannot go in Class 3, and therefore it falls under Class 2. So those are the most common. They're pretty much 95% of the landfills, okay, in Alberta, of the Class 2 kind of landfill. And the Class 3 is fairly inert, okay, if you have, if there's, construction materials, so which mean that waste that's not putrescible, that's not going to biodegrade, okay, cement and so asphalt, so on and so forth, we go into Class 3 landfill. So let's put a functional definition on leachate. So how can we define landfill leachate? All right, so a functional definition, it's a wastewater, okay, which is essentially qualitatively, okay, in terms of its characteristic, so on and so forth, and also quantitatively, the volume will vary from one landfill site to another one, but also within the landfill sites, because you have the footprint of your landfill, but you also have the cells, okay? So that also make up the landfill. So you're going to have several of them, okay? And the qualitative and quantitative variables may also vary in that regard. So that make it very, in terms of landfill quality, the quality of the landfill, the quantity of the landfill, somewhat, very unstable in terms of try to predict, the quality and also the quantity that might be generated over time. All right. So, and also one of the things in terms of the landfill leachate, it changes, but typically speaking, when we look at it from a scientific standpoint, the changes, because the cells themselves, when you look at them, they're like a bioreactor. Okay, so as a result of that, if you look at this here, so if you look at the quality of the quality of the landfill, the characteristic of it, that's one that's very young, from a very young cell. Okay, that's an older one. All right, so as you could see, the color is different, and also this one here, it's also a little bit different. But and the reason for that is because under the decomposition taking place in the cell, it's under both aerobic and anaerobic. So therefore, the constituents over time will change because of the dynamic occurring in that case, we can call it the bioreactor. So how did we approach that? So we did some analysis. Okay, so in that sense, in terms of data collected, from both primary and secondary sources, and also information that we got from freshwater resources, in terms of lakes and river. And from there, we drew some inferences to determine if the leachate chemistry exceeds regulatory limit. Now, as already I alluded to, from a regulatory standpoint, all right, any parameter that exceeds, okay, could result in non-compliance with current Alberta and other jurisdiction requirements. So that's very important in terms of when we're conducting the study. So limitation, delimitation, and assumptions. So let's start with assumption here. So we assume that the selected rivers and lakes are representative, okay, of or similar to freshwater in the formulation of the WBDF in terms of the chemical and physical properties. So we also generated some secondary data, all right, and from in terms of standard operating procedures, from sample collection, analysis, and reporting, and the limitations. So this was very, very important in terms of setting up the boundaries. Okay, so but we made use of the knowledge we had, and also the convenience in terms of having access to identifying requests and obtaining some of that information pertaining to leachate from Alberta government, and we combine those data from similar landfill tax, okay, municipal data, all the data from landfill tax, all the data from Alberta government. So we categorize them as municipal. We put all the municipal landfill under one umbrella, and industrial landfill, and also all fill. Okay, so essentially that gives us three types source of landfill leachate. Okay, and we combine them in each case, and we analyze it and look at whether or not the data are normally distributed, and also from there most of it is normally distributed, and be able to do some statistical analysis, very, very descriptive statistical analysis. So, and some of the limitation. So we assume that we had a sample size, okay, that should be, representative enough in terms of be able to do a generalized conclusion, okay, and the result that we get will be meaningful, and in that sense can be applied, okay. And also obtaining access to enough municipal oil and gas and industrial leachate secondary data. So those are some of we didn't look at all the parameters that we get from the information requested, okay, and also some of the analysis that we also got conducted. So by talking with some of the experts in that field, i.e. Amaco, and also talking with Baker Hughes. So we focus on the following parameters, in terms of pH. So that's the recommendation they provided. So okay, focus on those ones. Electrical conductivity, we look at soluble salt, and individually, i.e. calcium, magnesium, sodium, potassium, nitrate, nitrite, and TDS, also alkalinity. We look at bicarbonate and carbonate and hydroxyl, and also look at hardness and also sodium adsorption ratio. Okay. So as already alluded, so here's the rationale behind that, because in the interactive nature between drilling fluid and the subsurface, okay, testing of those parameters essentially were very, very important in order to assess, what will be the potential impact on the effectiveness of the on the drilling fluid, whether or not the performance of the drilling fluid will be affected, and if it's going to be affected from a chemical physical standpoint of the leachate stream. So those are the parameters which were recommended. Okay, fresh data water collection. All right, look at it. So those are the sources here. So we got that pretty much, around Alberta. Good. Okay, so we have 4 lakes and 4 rivers across the province. And in terms of the leachate, so we have several sites. All right, 5 leachate sample primary data and 7 leachate data sets primary data, and some information. Okay, those are municipal, industrial, all field. Okay, in terms of primary and their location. So this is a bit of some information on the primary leachate data. All right. So the main thing to keep in mind is that the samples were handled, by following appropriate field QA/QC, and all the lab analysis were performed by a third party, which is a licensed commercial lab. So now, in terms of secondary data, some of the important information we got in that sense, I would like to highlight here. Still, from as I will present in the as we move forward in the presentation, and some of so how we went about determining the volume of the leachate generated in the province. So we use that information from the secondary data, because the landfills, they have to record, most of them collect the leachate, and they also have to report to the government, so how much leachate has been generated, okay, for that year. So what are some of the statistical analysis that we perform? We look for outliers, box plot, equal variance, the ANOVA analysis, they're very typical, and descriptive statistics. All right, so we use as our dependent variable, we use the parameter of interest, okay? And this was carried out at 95% confidence interval, significance at 0.05, okay? So whereas for the primary leachate, okay, so what we've done, we subjected them to some regression analysis, and we did some graphical representation here in terms of classifying the water chemistry using Piper diagram and measurement of pH and EC. This was really interesting, and we wanted to see by adding, by adding the fluid substance, the additives to the leachate, how this will impact the pH and also the EC. So we did it only for 2 type of additive material. So it wasn't that comprehensive, but nonetheless very insightful. So what we got out of that? All right, so total, all the descriptive statistic, we've done that on about 78 landfill, okay, from 8 Alberta sites, and about 200 of them freshwater data set collected from 8 Alberta rivers and lakes over the years. So there was a lot of data we had to handle. So what this is really our finding here. So when we did that, this is how we arranged the data: water type and number of samples, the mean, all right, and the range, and standard deviation, coefficient of variation, and confidence interval, as I pointed out. Okay, lower level and upper level, upper limit, lower limit, upper limit. So that's pretty much, from a result standpoint, what we got is that industrial, municipal, and oilfield leachate. Parameter of interest mean value, okay, exceeded tier 1 criteria for EC, sodium, and chloride ions, TDS, carbonate, and also SAR. Okay, whereas freshwater sources for the lakes and river, the mean values exceeded pH, EC, sodium, TDS, and SAR. And interestingly enough, when we look at industrial, municipal, and oilfield leachate, mean value exceeded all freshwater source mean value only for calcium, magnesium, and hardness. So typically speaking, the carbonate values for the leachate kind of water type were less than the maximum lake mean concentration average. All right, so source comparison here with the ANOVA analysis at the significance level of P less 0.05. So what did we find? We find industrial, municipal, and oilfield leachate were significantly different to freshwater sources for EC, calcium, chloride ion, nitrate, carbonate, alkalinity, and hardness. And we also noticed some leachate type exhibited similarity to freshwater resource. That's the big picture as it relates to pH, magnesium, sodium, potassium, sulfate, nitrate, and bicarbonate, TDS, and SAR. And leachate types were similar for all POI, parameter of interest, except for SAR, okay, which is sodium adsorption ratio, so which means the relative concentration of sodium relative to calcium and magnesium concentration, okay, in the solution. So this is a little bit of the water chemistry classification here. All right, so that's pretty much what it looks like. So pretty much here, when you look at, start at the bottom, river. So they're pretty much the same type. And Lake 3, 4, pretty much Lake 1. Lake 2 is a little bit different, okay? And oilfield, in terms of the leachate itself, so it's a sodium chloride ion type, all right? And when it comes to industrial landfill, it's a mixed kind of calcium, magnesium, and chloride ion type. And for municipal landfill, it's a mixed calcium, sodium, and bicarbonate type. Okay, so what we've done, though, put that information, okay, on the hydrochemical phases, all right, and that's pretty much what it looks like. Okay, so when you color code it, so it's pretty much, as you could see, the distribution in terms of for the different landfills. Okay, so based on the phases here, so we say there are 3 groupings. No single cation and ion pair greater than 50%. So which means that in the leachate itself, so there is no single, be it calcium, magnesium, okay, cation or anion, nitrate, or sulfate pair, which represent a concentration greater than 50%, okay, of the other cations and anion, okay, in that matrix. And carbonate hardness, the same thing. All right, so we have greater than 50%. All right, so and non-carbonate alkali for the oilfield, landfill. So we have non-carbonate alkaline about greater than 50%. Okay, so the important point is that that leachate with similar water chemistry classification, essentially we anticipate in terms of will behave very similarly to if you were using, in the WBDF, if you were using fresh water. Okay, so. So we also did some linear regression, and this was really, really interesting in that sense. To look at if we have very strong correlations between the leachate strength and versus the parameter of interest. Okay, so everything, there is also another page, but I only use a portion of that information here. As you could see, the correlations are, you come down here, the correlations are very, very, very strong, okay, in terms of relationship, right? So what those allows us to do, though, so any kind of parameter of interest, using the linear regression for a specific type of landfill, we can plug it into the equation, okay, i.e. that would be y, and then we can solve for x. So that will tell us essentially by how much that parameter of interest, okay, I mean the strength of it, i.e. by how much we'll have to dilute it, okay, in order to meet Alberta Tier 1 criteria. So, and that's the value here on the last column. But it's also interesting to know a lot of time when you're dealing with drilling fluids, so you also have to make adjustment. And in terms of pH and in terms of some other chemical requirement in order to make the fluid more efficient. So the inference talking to Baker Hughes and Amaco, I say that even though the leachate itself exceed, but on the other hand, so what does that translate into? It means that perhaps in terms of how much chemical they might have to use in order to make some adjustment, that can be significantly reduced. So essentially, it's a blessing in disguise, kind of. Okay, so it's a little bit more beyond the criteria, but also there's also a matter of practicality in that sense when you look at it a little bit deeper. All right. So as I mentioned that, so you having that GLM, okay, so a very simple generalized linear model. So we've been able to do some assessment in terms of the strength of the leachate. So the bottom line is that all leachate sources will require some kind of dilution, okay, of different degrees in order to achieve Tier 1 criteria. Okay, so but nonetheless, by exceeding this also from a chemical input standpoint, this may also reduce the need for adding chemical, okay, in terms of improving the effectiveness of the drilling fluid. All right, so this is where we did a little bit of test here in terms of we used two drilling additives, which are bentonite regular and pack regular. So we added, so we have our samples, okay? So we have our leachate here. And we added the additives. And that's pretty much what we've noticed. So a little, the pH went down in all, with all the leachate sources. And some other instances, so we have the EC increases and also EC decreases, all right? So, but also very, very important, I'll come back to this here. So all the leachate sample, okay, with the drilling additives, shows some, when we added the additive, which also showed some level of flocculations, which is essentially which is desirable when you have your drilling fluid. And a lot of time, in order to improve that flocculation, you might have to add calcium. You may also have to add barium. So what does, as already alluded to, by having the landfill having certain characteristics, so you might have less of an input, of those chemicals. So which means that the cost of chemical could be meaningfully kind of reduced. So in this here in the system, what we think is happening is that first and foremost, when it comes to the drilling additives, so we don't really know, what essentially the information is proprietary, okay, and that's the way it is. So we don't really know the formula per se, but we assume that the pH is decreasing here, and what is happening is that you might have production or release of hydrogen ion or a decrease in hydroxyl, okay, and concurrently you also have release of some ions into the matrices, and in this case here you will have a decrease. And this one here, it's and I think you have a decrease, and that's the samples here, site D and E. This is where you use bentonite, and bentonite, as we all know, it's a good absorbent, so they'll be more likely to remove some of the ions from the matrix more significantly than packed regular. All right, so let's talk about leachate estimation. So this is where it becomes really very interesting, because from there we can demonstrate that there's a lot of leachate being produced. So and more than enough being produced, and we're not going to have a scarcity of it when you try to make a business case to the oil and gas sector. So we looked at it, and we found out on an annual basis, about 140, we have about what? About 143 millions, okay, cubic meter, and it's a big range, which should be expected, okay, and because of the variation in size, but also variation in weather conditions from when you compare the northern part of Alberta or the southern part of Alberta to the northern part of Alberta. So we tend to have more precipitation in the northern part than we tend to have in the south. Okay, so this is a big range. All right. So, and if you look at the amount of fresh water allocated in 2016, it was about 10 millions. And as I mentioned, we estimate on an annual basis there will be about 140 millions available. So therefore, the annual leachate volume significantly increased the amount of fresh water requirement. Okay, in that sense, from a quantity standpoint, it doesn't seem to be problematic. Okay, but from a drilling standpoint, all right, so the drilling fluid must be non-toxic. This is according to the regulations. But in our little investigation, we didn't look at the biological aspect that could be associated with the leachate in terms of potential presence of pathogens, all right, and also in terms of the toxicity, okay, of the leachate per se. But nonetheless, though, when they do drilling, oil and gas, a lot of time they have to control, bacterial growth and all that stuff. So they use sodium hypochlorite. So in that sense, we think that all the pathogens per itself, it's not really a risk, because this is something which is already practiced. They can use the same approach here to control the presence of pathogens. All right, from a toxicity standpoint. Now, that's why Alberta regulators, Alberta environment, like the fact that the drillers, the oil and gas using fresh water, because they're very concerned about contamination of the top 150 meter, because that's where a lot of their fresh water is. So therefore, they take that approach to provide groundwater protection. But below 150 meter, so this is where, in that case, we can use the leachate, because there is no Alberta regulator doesn't prescribe anything specific in that regard. Okay, so we can use that below the 150 meters. Some of the concern also from an environmental standpoint already alluded to groundwater, the aquifer contamination, but also when you drill, you're going to generate what is called the drilling waste. And in terms of how you're going to dispose of it, so it's also function in terms of the level of contaminations, and also what's the most practical way of in terms of that drilling waste could be handled. So if we look at the disposal methods here, all right, so we have MBC, and typically speaking, that's the old-fashioned way. We use very little of it, and I think that wouldn't be a problem, okay, in terms of potential for contaminations, but that's something we'll have to keep in mind. But and you have off-site disposal, and this is the most common one, which is used nowadays. It's the LWD, which is land spraying while drilling, okay, or land spraying. And essentially, when we land spraying, it's on site, and land spraying and LWD, it's pretty much off site, okay? So there might be some concern. So therefore, some some environmental assessment have to be conducted and make sure that all the precautionary measures are handled properly, all right? And also another concern when we did those disposal methods, there's also some concern in terms of runoff, all right? And if you have some contaminant exceeding criteria, and also leaching from land spraying, so leaching from the vital zone into the groundwater, those are also some concern that have to be addressed. So the study doesn't really provide definite answers, but it sheds some light in terms of the potentiality of using landfill leachate, okay, in oil and gas development. There's some other issues that has to be addressed, and we're working on that, and also with the regulators. So what are some of the challenges that exist when you do something like that? There's always some challenges. So if we look at them, so landfills are dispersed, and Alberta precipitation, as already alluded to, it's further in the north and the west, but that's fine because a lot of oil and gas activities is in the north, okay, that's fine. And now whether or not we're going to use a centralized location to bring, the leachate, or the leachate is going to be transported, okay, to a specific location. It's being transported, so you might have risk, all right, of spills, okay. And the yearly fluctuation, I don't look at it personally as a problem, because we produce more than enough leachate, okay. So compared to the amount of water used, so it's a concern nonetheless, okay. And factor now, which is a little bit beyond, which is a little bit less technical now. It tends to be a bit more of the soft science. So in that case, social acceptance. But I think there is an appetite for that, because people are promoting, sustainability, and what better way to, for oil and gas to demonstrate they're being sustainable. And instead of using fresh water now, they're using, they're using wastewater. Okay, so that's one way to somewhat boost the image, and also very importantly, this is where the regulators come into play. All right, so the regulators, they started looking into it because they start feeling the pressure. It's to promote, encourage, and also be visionary in terms of how they can come up with regulations or guidelines, okay, that will facilitate the use of landfill leachate by the regulators. And also from the economic standpoint, and I think that makes sense though, because the cost of using fresh water is extremely expensive, and therefore the wastewater, the cost will be very minimal. Okay, perhaps transportation costs, and that might be it, and that would be a significant saving for the oil and gas sector. All right, so that's a nice segue into that. If you look at the cost-benefit analysis, all right, so you'll have all those all three factors, and essentially in a closed-loop kind of way, dynamic, if you prefer, the ecological, the social, and also the economic. So when you look at it for the oil and gas using, landfill leachate, okay, as a source of water, essentially, all those from a sustainable resource standpoint, they cover all those three important points. Okay, all those three important points essentially get optimized. So from a cost standpoint, all right, so if we go straight down to the bottom here, so how much that will save, on an annual basis, okay, the oil and gas sector, if they were using landfill leachate. So essentially, that will save them about $320 million on an annual basis. So even though if it's half of that, still a very significant kind of savings in terms of, like I said, the bottom line is very important, because this is, if you look at in terms of the concern of the oil and gas sector, is pretty much two things: the regulations, and also what does that mean for them in terms of bottom line. And from the bottom line standpoint, so it means that they're going to be saving a lot of money. So limitations, all right. So like anything else, so we have limited data, empirical data, all right, to go by, but and also very limited published research data on that in terms of landfill leachate being used in oil and gas for drilling activities, and also, as I mentioned, we didn't include toxicity and pathogen, okay, assessment, but we don't look at it. We don't think that's really a big issue, okay, so that's not going to be a deal breaker. And what could be the other issue will be stigma associated with landfill leachate, and particularly, the oil and gas sector itself. Okay, so they're warming up to the idea, and the reason they're warming up to it, it's going to be, in the future, in the foreseeable future, the regulation is going to change, because using fresh water, it's becoming non-fashionable, so it's going to be very difficult, and to get licensed for that, and it's going to be also extremely expensive. Okay, and in terms of precedence, so landfill leachate has been used, okay, as makeup water in fracking operation in Alberta, and successfully. Okay. Okay, so from a regulatory standpoint, so those have listed some of the things that that could be done in order to promote landfill, the use of landfill leachate in the drilling program, create a provincial database, and do some data, so you can generate some empirical information, and from there, from the lab, move it into a bigger scale, establish a pilot project, and also use flexible kind of managerial approach, and by providing some kind of input from stakeholders. And once you get the information, the empirical information, and disseminate it, have some conferences and stuff like that with stakeholders. And what I mean by stakeholders, it's not only oil and gas, but also the general public, okay, and academia, so on and so forth. And also be dynamic in terms of policy change and evolution, So which means that review continuously and adapt and make it a little bit easier for for the oil and gas sectors in terms of adopting the use of landfill leachate in their operations, and also comprehensive cost-benefit analysis. We provided some cost-benefit analysis, but can do a little bit, more granular in that sense. And because we're not economists, but that can be done a little bit at a more granular level. In summary, landfill leachate is its sufficient volume, as already alluded to. The characteristics vary from site to site, but nonetheless, okay, it can be used, and it also have some. There's some good part, there's some bad parts, okay. And the chemistry and concentration of constituents of concern can be managed with chemical additives and additions. And incentive to reuse landfill leachate, it's becoming more in the limelight, a lot more interest, okay, and increasing escalation of freshwater scarcity, and also a lot of pressure from community, and also from a cost standpoint. Okay, stakeholder leadership is crucial, and in that sense, particularly from the regulators, and everyone should be, the drivers of that. And the leadership is very, very, very important. And based on the brief cost-benefit analysis, there's significant benefit in it for oil and gas producers in terms of using landfill leachate. All right, so that's the end of my presentation. So if there's any questions, I'll try to entertain them.